In standard geometry, compact sets behave exactly as you expect. They trap everything inside. But in higher dimensions, that perfect containment shatters. The physical intuition we rely on in basic calculus and linear algebra fails when we cross the boundary into functional analysis. To understand why this happens, we have to transition from those early assumptions to the rigorous, infinite-dimensional proofs laid out by Erwin Kreyszig. The ultimate test of a mathematical space isn't its shape, it is how an infinite sequence behaves when forced to move within it. This sequence breakdown identifies the precise limit where the tools of standard topology become insufficient for functional analysis. We first need to establish the environment. A normed space is simply a vector space equipped with a strict measurable concept of length, a norm. Next, we have finite dimensional spaces. Using standard 3D space as a model, this means the environment can be fully mapped out by a finite number of basis vectors, like x, y, and z. Then there is completeness. A space is complete if every Cauchy sequence, a sequence whose terms get arbitrarily close together, successfully converges to a point that strictly exists inside that space, leaving no missing gaps. Finally, we have subspaces. These are independent, self-contained vector spaces nested entirely within a larger vector space. These 4 rules govern the mechanics of standard geometry. We lock them in now because we will use them to break geometry in infinite dimensions. Conceptually, compactness acts as a topological trap. It forces an infinite sequence to eventually settle down into a predictable location. Kreyszig formally defines this as sequential compactness. It dictates every sequence must contain a subsequence that converges to a limit. This intense crowding represents that subsequence. Trapped inside the space, it has nowhere else to go and is forced to accumulate at a single point. For this trap to function, Lemma 2.5-2 states a compact subset must inherently possess 2 properties, closed and bounded. If the set is not bounded, the sequence simply escapes. It marches outward endlessly toward infinity, never forced to crowd together. If the set is bounded but not closed, the sequence converges to a limit right on the edge, a limit that does not technically belong to the set itself. Boundedness physically stops the sequence from escaping. Closedness ensures the final limit point is actually captured within the net. In finite dimensional spaces, the converse is flawlessly true. Theorem 2.5-3 states that a subset is compact if and only if it is closed and bounded. The Bolzano-Weierstrass theorem proves this by continually dividing the space. By halving the space and zooming into the section containing the sequence, you inevitably pinpoint the limit. This slicing mechanism works because it traps the sequence dimension by dimension. There are only a finite number of axes to constrain, but this perfection creates a cognitive trap. It leads students to falsely assume that being closed and bounded guarantees compactness in any space. Relying on this finite intuition guarantees a failure in logic when transitioning into advanced functional spaces. To see where the logic fails, we have to enter the infinite sequence space known as little L2. Let's set up a sequence of standard basis vectors in this space, starting with E1 along the first axis. If we measure the distance between the tips of the first 2 vectors, the result is exactly the square root of 2. When we measure the distance between the second and third vectors, the result is identical, the square root of 2. Every basis vector has a length of exactly 1. They sit perfectly within a bounded unit sphere, and the set is closed. Because the distance between any 2 vectors is always the square root of 2, they never get closer to each other. This fixed distance prevents crowding. No matter how far the sequence goes, no subsequence can converge, even though the space is closed and bounded. Infinite dimensional spaces have infinite geometric room. A sequence can step into a new dimension every single time, never accumulating at all. How exactly do infinite dimensions mathematically generate this excess room? The answer is Rie's lemma, which formally proves the mechanics of this spacing. If you have a closed proper subspace, like this 2-dimensional plane, you can construct a new vector of length 1, pointing out into the larger space. This creates a measurable gap. The distance from the tip of that new vector down to the closest point on the plane below will always be greater than or equal to a constant, theta, which is nearly 1. The lemma states that for any closed proper subspace, you can always find a vector of length 1 that sits at a significant distance from every single vector inside that subspace. The logic is structural. You pick a vector outside the subspace, measure its distance to the subspace, and scale it. That strict mathematical operation guarantees the gap. Ries's lemma serves as an engine. It mathematically guarantees that there is always enough room to step up and away into a completely new dimension, without touching the ones you left behind. That geometric engine leads directly to Theorem 2.55. It states that if the closed unit ball in a normed space is compact, that space must be finite dimensional. By generating a second vector orthogonal to the first, we can measure that they maintain a strict distance of greater than 1/2. In an infinite space, this iterative building process repeats endlessly. You can continuously populate new axes while strictly maintaining that minimum distance from every prior vector. This creates an endless sequence of vectors that can never converge, which means compactness in that unit ball is mathematically impossible. Theorems 2.5.6 and 2.5.7 rely entirely on compactness because it is preserved by continuous mappings, and it is the exact property that guarantees a function will hit a maximum and minimum value. Testing the compactness of the unit ball is the definitive boundary check separating standard linear algebra from the infinite dimensional reality of functional analysis. We are left with a stark dichotomy between two mathematical realities. Being closed and bounded perfectly traps a sequence, provided you only have a finite number of dimensions to trap them in. But infinite dimensions provide too much room. They allow sequences to wander endlessly, stepping at fixed distances into new axes without ever breaking the boundary. If you want to see complete visual explanations of the theorems inside Kreyszig, Rudin, real analysis, and topology, be sure to like, subscribe, and share this video. Let us know in the comments which specific theorem, proof, or chapter you need visualized next. Functional analysis requires a departure from physical intuition, replacing it with the formal mechanics of infinite dimensional sequences.